Hello, GraphQL Summit, and everyone on the live stream. Matt just shared with us the modern client stack. Suppose you're at the point where you're convinced that GraphQL and Apollo are right for you, as you should be, but you're looking at your code base and wondering how to get from point A to point B. My name is BUNGE, and I'm a front-end software engineer at Airbnb. I'd like to share with you some on-the-ground tactical tips for migrating to Apollo and GraphQL at scale, incrementally, and without regressions. Changing the underlying data fetching infrastructure of a large code base is challenging. There's a lot of code to migrate and users who would be affected if anything were to go wrong. We've been through the migration process on several teams at Airbnb and collected lessons along the way that we hope to share with you in case you're navigating a similar situation at your organization. First, we'll recap the progress we've made adopting GraphQL at Airbnb, strategies we've used for migrating, and exciting projects in the works that leverage Apollo and GraphQL. At last year's GraphQL Summit, Adam Neary, shout out in the audience there, shared how we're using Apollo and GraphQL to be ridiculously productive on the front end. We've made a lot of progress since last year to bring these benefits to more and more teams. This year, a small, scrappy team of engineers from across product and infrastructure banded together to rewrite our mobile web experience as a PWA, or progressive web application. The new experience drove enormous gains in page load time and provided a much more intuitive experience for the user. We also used it as an opportunity to roll out more GraphQL. As sections of the experience were migrated to GraphQL, we saw a steady increase in production traffic to our GraphQL gateway. Mobile web was a driving force here, but we also saw adoption across our host tools on desktop. iOS and Android engineers are working on rollouts for their platforms as well. Today, around 5.8% of all production traffic on Airbnb is using GraphQL. And that number will likely exceed 10% by the end of the year. Among the first product surfaces to have been migrated are search, our product detail page, and the booking flow. Work has already begun on a single guest platform with tooling to drive productivity across 7 product surfaces in the guest flow. That's awesome progress. But how did we get there? Let's look at some migration strategies we've used. The most common tech stack we're coming from for these migrations is a combination of REST endpoints, React, and Redux. And the amount of code and projects we've migrated ranges anywhere from 30,000 to 90,000 lines. What we'd like to use instead is React paired with GraphQL and Apollo. We have a few options on how to get there. The first is that we could rewrite our app from scratch. This sounds awesome, right? It's always so tempting, but it's rare that we get the chance. But we have been lucky in some cases, timing it with redesigns or the start of a new project. However, it's not always an option given time and resources. Plus, the institutional knowledge encoded in a large app takes a lot of time to get right and unwind. Instead, we could stop and refactor our app, and we've seen this work well on small or solo teams. The risk, though, is that it's painful to reconcile a long-lived fork or feature branch when there are many developers actively working in the repository. And the more changes we make in isolation means the more place for bugs to hide, and we don't want that. The final option we've used is an incremental approach. We found this to be the safest and most feasible option in most circumstances, given a large team and a large pre-existing code base. So let's delve more into how this has worked. We'll break down the process into 5 stages. Our goal at each stage is to have a shippable, fully functional, regression-free version of our app along the way. But before we begin, some prerequisites. We'll want a GraphQL endpoint on the back end. I won't cover how Airbnb moved to GraphQL on the back end, but you can check out this Medium post on the Airbnb engineering blog if you're interested in learning more. The second is that we wanted to use TypeScript on the front end, because we can generate TypeScript types for our queries directly from the schema, which is a single source of truth between the backend and the front end. We saw TypeScript as an absolute must in order to take advantage of end-to-end type safety. Development is faster, and we have more confidence in what we're building. We run a customized code generation command internally, but this is what you'd run as part of Apollo's tooling. This example shows a GraphQL query along with a TypeScript type that gets generated by Apollo's tools. We use this type in our code to make sure we're using the right values and have all of the necessary null checks. TypeScript is now the official language for web development at Airbnb, and over half of our 3 million line code base has been migrated so far. If you're interested in learning more about our process, you can check out this JSConf talk from earlier this year. When we're introducing GraphQL and Apollo to our projects, we first run an internal migration tool to convert our code from JavaScript to TypeScript first. And this talk covers that tool in a bit more depth as well. With a GraphQL endpoint on the back end and TypeScript in place, we need to swap out our REST request for a GraphQL request. As a side note, I will note that Apollo link REST is an option that allows you to use a REST endpoint with Apollo's front-end libraries. We preferred a GraphQL endpoint, though, in order to get TypeScript type generation and smaller response sizes via field selection. But you might consider it if exposing a GraphQL endpoint is simply not an option. The goal at this stage is to verify that our front-end back-end integration is working as expected and to generate TypeScript types. We won't make any changes to our React components or change the shape of the API response. This stage is just intended to affect where we get our data from, not how it's used. Let's use our homes checkout flow as an example. There is an endpoint for creating a reservation that has been exposed as a GraphQL mutation. We make our request using the Apollo client directly at the same point in the code where we were previously making our post request. The first thing to note here is that we said we're going to keep the API shape the same. So we need to construct a GraphQL mutation that corresponds to the data that we were previously getting back from our REST endpoint. Let's see what that response looks like. Ooh, that's a lot of JSON. Ooch. Well, we definitely have some opportunities here as far as overfetching. For now, though, our goal is to construct a GraphQL query that corresponds to this data. We could try to eliminate fields now, but we'll likely break something because we're not sure which fields are actually in use. GraphQL requires explicitly declaring which fields we need from the API. So we'll need to exhaustively list out every one of these fields from our GraphQL schema to match that response. Doing this by hand would be tedious and error-prone. Fortunately, we can leverage the GraphQL schema itself to help us out. Another place where we've seen the GraphQL schema in use is the GraphQL Playground, which is an awesome developer tool that makes use of this schema for autocomplete and tooltips. It's very helpful when you're authoring a query. Behind the scenes, the Playground issues this introspection query against the GraphQL server to get information back about the fields that are available. We can use this information for our purposes to recursively unpack the schema, because what we're trying to do is like a programmatic version of auto-completing at every level along the way. Another thing we'll keep in mind is a lesser-known feature of GraphQL that you might find helpful. GraphQL aliasing lets you arbitrarily rename fields in a query. We found this helpful because our REST endpoint exposed fields as snake case, and our GraphQL endpoint exposed them as camel case. So we could use aliasing to actually convert the case as part of our query, and this would get carried over into the generated TypeScript types as well. With these ideas in mind, we wrote a script to generate an epic 660-line mutation for the homes checkout flow. Here's a link to a gist with the approach if you're curious more about how this worked. We then run Apollo CodeGen to generate TypeScript types for this mutation. This is incredible. We get 1,000 lines of types straight from the schema. This is such a dream compared to how we do it before. We would look at the response, write up the type by hand. It would have mistakes. It would get out of date very quickly if the backend changed. So this is just a dream. Another thing to notice here is these adapt functions. There were slight differences in our request and response formats on the back end, so we created adapters on the front end. Adapter here doesn't mean anything GraphQL specific. It's just a utility function that transforms or adapts an object from one format to another. For the inputs, we made sure that the adapted request matched what the GraphQL endpoint expected. And for the outputs, we made a request to both the REST and GraphQL endpoints and recursively diffed the adapted version of the response to make sure it exactly matched what we were receiving before. These adapters will be removed at a later stage, but the intention for now is to keep all of the code surrounding this API call the same. At each stage, we have a shippable app. So we can pause here, ship it, and our app will still work. The next thing we'll want to do is propagate our shiny new TypeScript types throughout our code. And the goal of this is to make sure that to use the generated types because they increase confidence at later stages in the migration process. We'll get compiler errors when things don't line up. We're not going to touch any runtime behavior here. We're only editing the types. We go through our code and replace all occurrences where we had an any type or no type or a manually created one with a generated type from Apollo. As awesome as these types are, a common issue we've run into is having to do deep null checks like this one. Thankfully, there's a npm package with a Babel plugin you can use called IDX that lets us express this idea much more concisely, while still being fully type-safe. And IDX is just a stopgap until JavaScript supports optional chaining, which is currently a stage 3 TC39 proposal and will be included with the next version of TypeScript. We can't wait because it lets you write code like this instead. Before, we were using the Apollo client directly to make our API request. Now let's make our code more idiomatic by using the React HSCs exported by Apollo. Aw, did I say HOC? I meant hooks. Hook, hawk. Anyway, the recent Apollo React hooks package gives us some new functions to use. We love hooks at Airbnb because they're easier to reason about, there's less boilerplate, and they work better with TypeScript. We're still using Apollo HSCs right now, but we're actively upgrading to use hooks. At this stage, our app is using the Apollo client, but we're still firing Redux actions, and components are using the Redux store. Apollo takes care of data fetching with loading and error states, so we can wean ourselves off of Redux for this purpose. We refactor our app to use Apollo's HSCs or hooks instead, and update our components to use data from the Apollo cache rather than the Redux store. We need to keep the Redux store around for now, though, because it still stores some information not yet in the Apollo cache, but its role has been diminished. One of the benefits of GraphQL is reducing overfetching because clients specify exactly the fields they need. We missed out on that with our mega query, so let's fix that by introducing more granular query fragments. At this stage, our query lives in our top-level app component, as represented by this little GraphQL logo. It contains all fields required by all components all the way down the tree. But the best practice is for components to specify their own query fragments because it co-locates the data needs with the code that actually uses the data. It reduces overfetching and promotes code reuse because fragments can be shared across queries. We start at the leaves. These are the components closest to what ultimately gets rendered, so we can trace through it and determine what fields are actually in use and add them to its query fragment. We rerun codegen to get types for our new fragment and use these types in the subtree of the code. We can actually use TypeScript to help guide us here, because if we've missed a field in our fragment, we'll get a TypeScript error at the usage site where it's missing. We then compose this fragment up into its parent component and one level further up back into the app component. This is a gradual change, so we're not done yet, but we have a fully working app and can verify the changes we've just made in isolation. We rinse and repeat this process until our whole tree is covered. Before, the app had an omniscient query that knew about all the data used by all the components in the tree, but now our top-level query is simply a composition made up of its child fragments. Because the fragments are declared in close proximity to where they're actually used, we can be confident that we're only fetching the data we need. Once all components have been migrated to Apollo, we can consider what to do about the remaining Redux state. We found that any state we were storing in Redux could be sufficiently managed by Apollo for API data and React's local state or context for client data, while considering Apollo's client local resolvers for more complex client data use cases. This gives us a consistent mental model for handling client data. We use React and Apollo for all state rather than fragmentation between React, Apollo, and Redux. Moreover, we found that we wrote quite a bit of boilerplate when using Redux for things that Apollo just handled out of the box. So we could delete substantial amounts of code when migrating to Apollo. And Apollo handled caching more effectively than our hand-rolled solutions did anyways. With all of these stages complete, we end up with our desired result of an Apollo and GraphQL-powered app that's 100% type-safe with no overfetching. And we kept the site up and running throughout each stage of our migration journey. With GraphQL powering more of our code, there are exciting projects that we're actively pursuing to take advantage of this new data fetching layer. I'd like to share 2 of them with you today. The first is service worker query prefetching. The goal is to kick off the GraphQL query request as early as possible so users see the page rendered with data sooner. Shout out to Callie Riggins, who is leading the charge on our mobile web service worker implementation and is pursuing this novel idea. Here's a side-by-side comparison of a server-side rendered page on the top and a page loaded via service worker on the bottom. If we don't have a service worker, our pages are server-side rendered. There's a long gap between the page while the page is loading before we see content. With service worker, on the other hand, an application shell shows up right away and allows the user to get oriented to the page while the content is coming in. And the page loads faster because more of our JavaScript is cached. Here's a profile of a request filled by server-side rendering. We start with the server request. This is when the server-side rendering happens and our GraphQL request is made on the server. Then we parse the HTML and download our JavaScript. At this point, the page becomes visible using the HTML that was rendered on the server. And once React hydration completes, our page becomes interactive. Here's a profile of a request fulfilled by the service worker app shell. The service worker immediately fulfills the request. JavaScript is loaded from the cache, and we start some initialization. The shell becomes visible, React hydrates, then our GraphQL request begins. The user sees a loading state until the request completes, then our page is interactive. There's a gap here, though, between when the service worker started fulfilling the request and when the GraphQL request began. There's a significant optimization opportunity here. We could register our queries at the route level instead of at the component level. Then the service worker could kick off the GraphQL request right away because it decouples the React rendering from when we can read the query. In this particular instance, that would have saved us 400 milliseconds. This means the user would have been able to interact with this page 23% sooner. And that effect size is even larger for slower devices. We tried this with 6x CPU slowdown, and we could see the page 50% sooner. This performance win is huge. And with this primitive of being able to load data just given the URL, we can do other fancy things like preload data for any link on the page. And all of this is happening off of the main thread. Another project we're pursuing is a unified schema. And shout out to Arun in the audience, who's been building out this system and piloting it on the trip planning team. To understand the problem this project is solving, let's first look at Airbnb's service-oriented architecture. Our backend services are broken down into 3 main categories: data, derived data, and presentation. Data services encapsulate a data model, like a listing or a user, and derived data services combine information from multiple data sources. For example, a listing card combines user and review data. Presentation services encapsulate the logic of an end-user experience. Clients call presentation services to get the data needed to render the page. Currently, our GraphQL schema is service-centric. All of the top-level keys correspond to presentation services. This was a concession we made so that GraphQL would be more compatible with our particular service-oriented architecture strategy. Though now that GraphQL has gained more traction internally, we're revisiting this design to make it more data-centric. The new schema would expose a unified graph that is more sensible for clients and would enable better client-side cache utilization because more entities are shared across queries. The same services are used behind the scenes, but it's more left as an implementation detail. To make this happen, our data-centric schema federates out to services that hydrate the data requested by the client. The data hydration code defines how to load objects by their ID. Centralizing our hydration logic reduces the amount of code that we saw duplicated across many of these different presentation services. Moreover, we can improve data fetching efficiency. There were cases where the same data was being loaded at various levels in our presentation layer. This is an example trace from a query made by our product detail page. Each bar here represents a service call. And the 10 purple bars represent redundant data fetching for the exact same listing. We can reduce data fetching inefficiency by batching and caching requests at the centralized hydration layer. That would have meant only hydrating that listing data once. This work is in beta, but we're encouraged by our early results and we will certainly have more to share by the next GraphQL Summit. I'd like to leave you with a few key takeaways. When Apollo is paired with TypeScript, you can build and migrate code with significantly more confidence that nothing broke along the way. Consider the options and decide whether an incremental adoption strategy is the best approach for your situation, if you need to change a large pre-existing code base and keep it up and running at every step along the way. Finally, Apollo and GraphQL are a client data foundation on which you can do amazing things, and I can't wait to see what you all build next. Please come find me or any of the other Airbnb engineers here who would love to talk with you more about any of this. Thank you so much.